Welcome back to The Explainer. If you're prepping for high-stakes software engineering interviews or, just looking to level up your system's architecture game, you are absolutely in the right place today. We're doing something really cool. We're bridging a huge gap. We're going to take that abstract, whiteboard algorithmic complexity theory and smash it right into the strict, modern systems-level reality of Swift 6. We're taking the math, putting it into code, and seeing how modern compilers actually deal with it under the hood. Let's get into it. Real quick, here's our roadmap for today. We'll hit the scaling problem, human intuition, visualizing growth, pseudocode and complexity, Swift 6 ownership, and finish up with memory safety. Section 1. The scaling problem. Okay, so before we write a single line of code or draw any charts, we have to ask, why do we even care about algorithmic complexity? When you write code that ingests data, the absolute fundamental question, literally the first thing a senior engineer will grill you on in a system design interview, is this: will it fit in memory and will it actually finish running? Because look, for a tiny dataset, pretty much any algorithm looks fine, right? But in the real world, we have to predict how code will handle massive inputs without actually running it and just waiting around to see if our servers crash. The tricky part here is that measuring time in seconds or memory in megabytes, that heavily depends on your specific hardware. A terribly inefficient algorithm might actually run pretty fast on a supercomputer, but that definitely doesn't make it a good algorithm. And that is exactly where Big O notation comes to the rescue. Big O lets us just throw hardware out the window entirely. Instead of clocking time, it isolates the single most critical factor in all of algorithm analysis, which is growth. It gives us this abstract way to say, hey, let's compare a logarithmic algorithm against a quadratic one, so we can confidently predict its limits as our data scales up to infinity. Section 2. Human intuition. To really get a gut feel for algorithmic scaling, let's actually step away from the keyboard for a second. I'm going to throw a basic biology question at you to set up a classic resource conflict. Why are cells microscopic? Like, why don't we have these massive elephant-sized single biological cells just roaming the Earth? Well, if you look at the spherical growth model here, it beautifully illustrates a perfect scaling failure. Let's pretend a cell is a perfect sphere. It absorbs nutrients from its environment through its surface area, which grows at a quadratic rate, big O of r squared. But here's the catch. The cell has to feed those nutrients to its entire internal volume, and volume grows at a cubic rate, big O of r cubed. So as the cell expands, that r-cubed resource consumption just completely blows past the r-squared resource intake. The inputs literally cannot scale fast enough to support the internal operations, and the cell starves. This is a physical bottleneck, and guess what? It's exactly what happens when your software algorithms have mismatched growth rates. Section 3. Visualizing growth. All right, let's transition from biology over to geometry to get a language-independent visual of how data actually scales. Check out this single green square. It has a side length of r and a total area of a. Think of this square as your baseline unit of work, maybe a single array or matrix operation for a really small data set. Now watch how this builds. If we just double our input size, stretching that side length to 2r, the area doesn't just double. No, it absolutely balloons. It quadruples to 4a. The sheer amount of work required just expanded way faster than our input grew. And if we push it further and triple the boundary to 3r, the area block blows up to 9 times its original size, 9a. This right here cements the concept of quadratic, O of r squared growth. It is so absolutely crucial to visualize this. Because when you're in an interview and you nest a loop inside another loop in your code, you are building this exact expanding square. You are creating a situation where a seemingly tiny increase in array data triggers a massive explosion in processing steps. Section 4. Pseudocode and complexity. Okay, with that visual intuition locked in, let's step into the formal mathematics. Don't panic. Look right here at definition 2.1. T of n is big O of f of n. So what does this formal math actually mean for us? It simply means that big O is a growth prediction. It establishes a relative pecking order among functions. We're basically saying that past a specific sufficiently large turning point, which we call n sub 0, some constant multiple of our function will always, without fail, act as an upper bound on the time our algorithm takes. It is not an exact formula, guys. It's a guaranteed ceiling for massive data sets. And because we only really care about that long-term ceiling, we get to take some incredibly handy arithmetic shortcuts when we analyze our code. We drop constant multipliers, and we just completely ignore slower growing terms. Why do we do that? Well, because a linear operation, even something crazy like 1,000 times n, might technically be slower for a tiny data set, but a quadratic n-squared operation, it will always overtake it eventually as n approaches infinity. When you're at scale, the highest exponent polynomial is quite literally the only thing that matters.
Let's map this directly to an actual algorithmic state using this matrix sum pseudocode. Picture a 2D array. We've got an outer pointer I, tracking our rows, and an inner pointer j moving across the columns. Inside, that inner loop just executes a simple addition. Boom, constant time, big O of 1. But because pointer j sweeps across d columns, that entire inner loop costs big O of d. Then, the outer pointer I repeats that entire row sweep n times. Multiply those nested boundaries together, and we arrive at our final time complexity of big O of n times d.
Section 5. Swift-6 ownership. Now, let's pivot from abstract theory over to strict compiler reality. Let's look at how a modern systems-level language maps this exact whiteboard math directly to actual machine hardware. Consider this add and reset loop taking in two variables x and y. In older compilers, or honestly in languages without strict exclusivity rules, every single iteration acts like that slow snail on the left, reading the value of y directly from system memory. Why? Because the compilers simply can't guarantee that x and y aren't secretly pointing to the exact same memory address. But Swift-6 enforces what's called the law of exclusivity. It mathematically guarantees right at compile time that variables being modified do not overlap. Period. Because of this ironclad guarantee, the compiler can optimize the loop using lightning-fast CPU registers instead of constantly fetching slow memory reads on every single pass. Your theoretical big O complexity is fundamentally protected by the language's own safety rules. Section 6. Memory Safety. Let's wrap this up by looking at how Swift-6 handles underlying state and resources without breaking our theoretical constraints. See, in a lot of languages, handling complex data safely comes with all sorts of hidden trade-offs. Historically, Swift relied on this copy-on-write illusion to manage value types, and that relied on implicit reference counting. But reference counting means runtime overhead. It's hidden work happening right behind your back. Swift-6, however, introduces non-copyable types, denoted by that cool tilde-copyable syntax. This gives you, the developer, granular, deterministic control over the exact lifetimes of your data. It just completely eliminates that hidden reference counting overhead, handing you true, verifiable, constant big O of 1 resource control right at the compiler level. So, I'm going to leave you with this somewhat provocative question to ponder. If your theoretical big O of 1 algorithm incurs unpredictable, hidden memory and copying overhead at runtime just because of the language you're using, is it truly constant time? The absolute beauty of the Swift-6 paradigm shift is how it perfectly aligns the mathematical theory of the whiteboard with the uncompromising reality of the silicon, giving you absolute deterministic performance. Thank you so much for joining me on this explainer. Keep analyzing, keep optimizing, and I'll catch you next time.